Welcome to my presentation. My name is Liang Zhou, an incoming research scientist at Facebook. This work was done when I was a PhD student at the University of California, Riverside. During my PhD, I worked with Professor Lex Mbuyan and Professor K.K. Ramakrishnan. The title of my talk is Gemini Learning to Manage CPU Power for Latency Critical Search Engines. Large data center is well known for its significant energy consumption. In 2018, Google's data centers consumed around 10,000 gigawatt hours of electricity, which cost them more than $731 million per year. Producing the electricity used by Google's data centers will result in the release of greenhouse gas emissions that are equal to those from around 1.5 million passenger vehicles driven for 1 year. Thus, it is essential to make data centers energy efficient. Power management for latency-sensitive applications such as web search is challenging due to the strict latency constraint. A search engine typically employs a partition and aggregate architecture in which the aggregator broadcasts the search request to all the ISNs. For improved search latency, an ISN has to return a query's response before the given deadline. However, ISN servers are typically lightly loaded, and the query service time is much smaller than its deadline. To save power, DVFS or sleep state techniques exploit this kind of latency slack to slow down or delay the request processing and finish its work just in time. In this paper, we concentrate only on the DVFS technique. Paxos and Rubik are two state-of-the-art DVFS schemes in the literature. In Paxos, it has a feedback design to select the CPU frequency at every epoch granularity. When a deadline violation happens, it will only boost the frequency at the beginning of the next epoch. Rubik develops a statistical model to change the frequency at every request arrival and departure. It assumes that all the request service times follow the same distribution and uses the tail of this service time distribution for determining the CPU frequency. In this table, we find that all the prior works use the past history or a single distribution to predict each query's compute demand in the future. However, the measurement results on a search engine with the Wikipedia query trace and index show that search request service time exhibit high variations. On the left two figures, the Wikipedia search workload in terms of requests per second has both long-term and short-term variations. On the top right figure, the service times of 3 consecutive requests across different ISNs are given. We can see that the query of Canada has 5 times longer service time than the next query, Bobby. In addition to that, the query of Canada has various service times on different ISNs. The bottom service time distribution also confirms that they have long tails. Thus, assuming a single distribution is insufficient for power management, this same distribution assumption in prior works might waste CPU power and incur deadline violations. We need a query-specific service time prediction. In this paper, we tried different prediction models. For example, a simple linear regression model can yield a 27% prediction accuracy. However, even the most sophisticated model of a neural network still cannot have a 100% prediction accuracy. In the rightmost figure, it achieves the highest prediction accuracy of 89% after 60 training iterations. With an inaccurate service time prediction, some requests might fall behind the deadline and violate the latency constraint. To solve this problem, we propose a novel power management framework for search engines called Gemini. In Gemini, we have a neural network model to predict each query service time and then develop an additional neural net model to estimate the error in the service time prediction. When a prediction error happens, Gemini can utilize a two-step DVFS to correct the error and catch up to the deadline. In the first step of our Debrief scheme, we select an initial CPU frequency based on predict server time. However, the prediction model might have some errors and make us fall behind the deadline. To avoid this, the frequency has to be boosted at a second step to catch up to the deadline. The major challenge here is about when we should boost the frequency to get a good balance between the energy saving and deadline violation. In our work, we design a statistical model to calculate the proper boosting time upon every request arrival and departure. Our work has some similarities to the stepwise Debrief scheme proposed in PACE. However, PACE still needs a work distribution for its linear programming model and is evaluated in simulation. Our Gemini, with only 2 steps, is implemented on real search engine with DVFS control in the user space. In our 2-step DVFS, we will adjust the current frequency configuration when a critical request arrives. A search request is critical if it will miss its deadline under the current frequency configuration. In this example, request R1 is non-critical and request R2 is critical. Request R2 will miss its deadline, D2, if we keep the current frequency configuration. To avoid the deadline violation, we boost the frequency for processing request R1 earlier so that the subsequent critical request R2 can begin to execute before request R1's deadline D1. Thus, we give more time for R2 to finish its work before its deadline D2. The case with n requests in the queue is similar. In the example, request R1 and R2 are non-critical, and the request R3 is critical. We choose an earlier boosting time, T1 prime, for request R1, such that the critical request R3's deadline can be met. To minimize the frequency transition overhead, only the current request being executed and the critical request use a 2-step DVFS, and all the other requests in between will execute at the current CPU frequency. In the next example, request R3 finishes its work and is going to leave the queue. Whenever a critical request departures, our DVFS scheme will find the next critical request and adopt a new 2-step DVFS for the remaining n-1 requests in the queue. Now we introduce our neural network predictors. In Gemini, we first need a latency predictor to get the survey time S for the initial frequency selection in our 2-step DVFS. An accurate latency predictor can produce a smaller prediction error and avoid boosting the initial frequency too early. Second, our DVFS scheme utilizes the prediction error E to calculate proper boosting time. However, it is impossible to measure during the runtime. Thus, Gemini employs a second neural network model for the error prediction. Both the latency predictor and error predictor use the same set of query features. This table lists all the query features that are used by our neural network models. All of them can be easily obtained from the ISN index. Whenever a search request arrives at the ISN, we extract its query features and then utilize our latency predictor to get the predicted service time. After having the predicted service time, we can compare them with the measured service times and get the prediction errors. These prediction errors become the training models, training labels for our error predictor. Finally, the 2-step DVFS in Gemini can leverage the prediction results from our error predictor to calculate the frequency boosting time. For model selection, we tried the model of linear classifier, neural network regressor, and the neural network classifier. Among these models, the neural network classifier produces the best prediction accuracy of 89%, with an inference time of only 79 microseconds. All our models are implemented by using the Google TensorFlow API. The 79 microseconds inference time is quite small compared to the tens of milliseconds for the request service time on our platform. Microsoft also reports that the request service time on Bing search is a few milliseconds. Finally, the last figure shows the prediction accuracy and loss results for our error predictor. The error predictor achieved a good prediction accuracy of 85%. Our framework is implemented on a platform with 12 CPU cores. We utilize the Linux ACPI interface for the user space device control. The frequency transition overhead on our platform is just 40 microseconds, which is very low compared to the tens of milliseconds for the request service time. The power management is achieved by using the RAPO interface. For search applications, we use the well-known Solr search engine. A complete dump of the Wikipedia web pages with 34 million documents are uniformly indexed across 12 ISNs. 3 query traces we used in our evaluations are the Wikipedia, Lucy netted benchmark, and track traces. The first result is from a trace-driven experiment. We can observe that Gemini has the best power-saving results on all the 3 query traces, with the lowest data violation rate. Specifically, we achieve 41% CPU power saving with only 2.4% deadline violation rate on the Wikipedia query trace. The next experiment investigates the impact of our neural network predictors on the CPU power saving. In this experiment, we developed 2 variants of Gemini, the Gemini 95 and the Gemini Alpha. In Gemini 95, we don't have any neural network predictors. For the service time prediction, we use a 95th percentile tail of a distribution. On the other hand, the Gemini Alpha only has the latency predictor, but uses the average prediction error in the past for calculating the frequency boosting time. By evaluating the variance on 3 different query traces, we find that more than half of the power saving in Gemini is due to the 2-step DVFS. By using the first latency predictor, we can improve the power saving result by 10.8%. With an additional error predictor, 6.5% more CPU power can be saved. Thus, both the 2-step DVFS and 2 neural network models are essential for our power management framework. In conclusion, in this work, we find that the service time prediction for search requests can never be 100% accurate. Thus, we develop a 2-step DVFS in Gemini to correct the prediction error. In our 2-step DVFS, we first select an initial low frequency to save power and then boost it at the second step for catching up to the deadline. We further enhance our 2-step DVFS with 2 separate neural network models, one for predicting the service time and the other for the error in the prediction. Finally, our framework is implemented in the Solr search engine and deployed on a real platform. Experimental results on 3 representative query traces show that Gemini can produce 41% power saving for the CPU with a very low deadline violation rate. Thank you for attending our presentation. This presentation and recording belong to the authors. No distribution is allowed without the author's permission.